All right, so this is question 4. It's going to be testing a specific function for binary search trees, which you learned about in lab 13. So basically, you have this provided class, which has left and right BST subtrees, and then you also have an int key. And this key is going to be basically the item at the root of your current BST, whether that BST is your entire BST or a subtree of your entire BST. And remember that BSTs have a recursive structure like all trees, and so you can take any part of your BST and it will still satisfy all the BST properties, which means the properties that you need to know are that, one, all the left children of the root, okay, and this also corresponds to of a subtree of a sub-BST, are less than the root. And then all the right children of the root are greater than the root, right? So these are the two BST properties that you need to really keep in mind for this question. So what we want to do is we want to fill in this number in range method, which returns the number of keys in this binary search tree T that are between L and H inclusive. So we're passing in the BST, and we're also passing in two integers that represent the bounds of our range within which we want to count the number of keys for. Okay, so this is where we need to write our code. So let's think about the base case, because the base case for these recursive functions tend to be pretty standard. So a common one is when T is null, right? So in other words, we don't have any more nodes in our BST. And in that case, we're going to be returning 0, because again, we're returning the number of keys, right? If we have no tree, obviously there are no keys that we can potentially check for. So, and because it returns an int, we have to make sure that we return 0. Right, so what if the tree is not null? So what if we do have some kind of nodes? Well, we first need to check the root, right? Because right now, the only value that we really have, that we really want to compare with L and H is the item at the very root of our BST or sub-BST. And so remember, in binary search, the whole algorithm is dependent on finding the median of your array and then determining which half of the array you need to look in to find your desired value, right? So the same concept applies here. So in this case, our median is going to be T dot key. That is going to be our median. And we want to see what its relationship is to L and H. So here are a few things that we should keep in mind. There are a few cases where as to where the key might be located within our BST. So here is case 1. Okay, so maybe the key is entirely in our left children. So for example, if we have a BST that looks like, I don't know. Remember that BST is a binary search tree, so by definition, all nodes can have at most 2 children. So maybe it looks something like this, right? Case 1 is where all the keys are somehow in our left children. Okay, so that means that, so what does this tell us about T dot key? So this key in relation to L and H. It means that the key is actually greater than the highest range, the maximum value, right? Because otherwise we would have to search also in the right children, but because we would already exceed the boundary, the upper boundary of our range, if we just look in the right half of our BST, we know that the keys must be in the left half. It must be, to be within range, it has to be smaller than H, which means that we're looking in the left half. So If T.key is greater than H, this implies, this arrow stands for implies, that we need to look in the left, right? Okay. And now what is case 2? It's the other extreme. So if our key is less than low, right? That means that we're not even in the range between L and H if we're searching in there, right? Because that's smaller than even the lowest bound that we want. And so instead, we need to look in the other half, which is the right child. So we need to look at the right branch of our BST. That's case 2. And now case 3 is when there's no clear-cut boundary between left and right children for our keys. The keys could be in the left, it could also be in the right, right? It could be somewhere inside, whoops, I did not mean to delete that. Undo. I don't know why it takes such a long time for Zoom to update itself. Okay. Yeah, so another case is when all the keys could somehow be somewhere in there, right? Instead of cleanly on one side. And so that means that we need to look in both the left and the right branch, right? Okay, so with that in mind, let's go ahead and start writing the code for this. So we know that if T.key is greater than H, right, we're going to be, it's kind of hard to write code on Google Doc. We're going to be returning recursively, right? We want to return the number of keys in the right branch. So that's going to, returning the number of keys is what number in range is defined to do. So we just need to pass in the left children, and then pass in the same L and H, okay? And I'll clear all this blue notation in just a minute after I finish writing all of this. Else, if T.key is less than L, then you need to do the opposite, right? You need to return number in range of T.right, and again, the same L and H. And then finally, if T.key is neither, outside the lower bound or outside the upper bound of your range, then you need to return both, right? So I'm just going to start with T.left of L and H plus, right, because we need to combine these two returned numbers of keys, plus number in range of T.right, and then L and H. And now, here's something that might be a little bit tricky to realize when you're first writing this. So if T.key is neither greater than H nor less than L, that means that T.key is within L and H, right? So I guess visually I can draw out what this means. So right now we have this range from, I'm going to draw it as like a number line because they're integers. So let's say we have L here and we have H here, right? If T.key is not greater than H, and if T.key is not greater than L, then we know that the key, T.key, is within this range, which is exactly what we want, right? And we say we want to find the number of keys in T that are between L and H inclusive. So what does that mean about T.key? We count it as one of those keys, right? So we count it. So that's going to be return 1 plus, and then all of that recursive call. Okay, so let me just make this a little bit nice. Yeah, so that is how your code would be. This is not the only correct implementation, although I can't really think of much differences in implementation. But this is a lot similar, very similar to the binary search implementation, the binary search algorithm.